Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. Our guest today is Professor David Spergel, who is the director of the Center for Computational Astrophysics at Flatiron Institute and Emeritus Professor at Princeton University. His research interests range from the search for planets around nearby stars to the shape of the universe. Using microwave background observations from the WMAP and the Atacama Cosmology Telescope, he has measured the age, shape, and composition of the universe. He's currently co-chair of the Wide Field Infrared Survey Telescope, WFIRST science team. WFIRST will study the nature of dark energy, complete the demographic survey of exoplanets, characterize the atmospheres of nearby planets, and survey the universe with more than 100 times the field of view of the Hubble Space Telescope. Welcome, David.
Thank you.
I want to start with the history of the universe. So from what I understand, David, something happened 13.8 billion years ago, perhaps some sort of quantum fluctuation, still open for debate. And that was the start of the universe and space-time as we know it. And it has been expanding ever since, possibly at varying rates. And one issue is that the cosmic background radiation, that's sort of the baby picture from close of the origination of the universe, and as well as universe today, look remarkably uniform. And that is one of the puzzles that need to be solved, right?
Absolutely. It's one of the remarkable things about the universe is its simplicity, both in terms of its composition. The universe, as we look out in different directions, looks like it's the same, has the same density, the same basic properties everywhere. And that's surprising in some ways, because if the universe started out expanding 13.8 billion years ago, is what our data suggests, and we look in the sky in the right, we look to the sky to our left, we look as far out as we can, we're looking out at regions of space that if the universe was expanding slower than the speed of light, so the expansion that we would expect in a universe filled with matter and radiation, those two parts of the universe have never had the chance to physically interact.
Yeah.
So that requires one of two things. Either the universe was uniform before this expansion started. We either had very special initial conditions that was uniform to a part in a trillion in a trillion in a trillion.
Yeah.
Or there was a pre-Big Bang theory that the universe underwent a period of contraction and re-expansion, so that the time did not start 13.8 billion years ago. That idea, by the way, while very interesting, requires modifications to general relativity. We need some new physics for that to be true.
That's Roger Penrose and others?
Penrose has, I think, Penrose's version is not very well worked out. that
Okay.
I think has been a very an incomplete idea. I think the work on the pre-Big Bang universe that I think has been the best developed have been ideas by Neil Turok at the Perimeter Institute, work by Paul Steinhardt and Anna Ias at Princeton and at Max Planck Institute. Those have been the best developed of those ideas. Though
Right.
those ideas are not the ones pursued by the majority of cosmologists. Most cosmologists are focused on an idea called inflation.
Yeah.
In the inflationary model, very soon after expansion starts, the universe becomes dominated by dark energy. This is something that we'll come back to. We know is happening now, but we think there was a very early dark energy dominance during the first trillionth of a second. This dark energy dominance drove exponential expansion. That exponential expansion takes a tiny volume that could be uniform and makes it as large as the visible universe. So that's one way of explaining the uniformity.
So one confusion sometimes general public has, David, is that when you say universe expanded at more than the speed of light, what you really mean is that it's not that the things are moving away from each other at speed of light. They are, but it's really the mechanism is that the space itself is expanding, right? So it's not a velocity issue. It's more the fabric of space-time is expanding by itself, right?
That's right. I think one of the most confusing features of general relativity for most people is the fact that space truly expands. And the image I have is, I think of a balloon that is expanding in size, and each galaxy is a little ant crawling on the surface of the balloon. So while the size of the ant doesn't change, the balloon gets bigger and bigger. This immediately leads to the question, what is the universe expanding into? And for me, the best answer is the future. So if I think of that image of an expanding balloon, that really the surface of the balloon is two of our space-like dimensions. The radius of the balloon, or how big the balloon is measured in time. So as the balloon expands, we're expanding into the future. And if I run the balloon backwards, and I think this is an important picture to have, as the balloon gets smaller and smaller and eventually contracts, you could see there's a moment in time at which the balloon collapses to zero radius. That moment in time is the moment of the Big Bang. So it's not, people sometimes ask, where did the Big Bang happen? And that's not the right question, because the Big Bang happened everywhere. Everywhere on the surface of the balloon shrinks to zero radius. It's when the Big Bang happened.
Right. So that image really works for me, David. The only thing people, I think, need to think about is that that's sort of a two-dimensional picture. So we have to imagine that the surface of the balloon, now imagine that in three-dimensional, our brains are not really capable of running that thought experiment. So this is an abstract notion in two dimensions, right?
That's right. It's a model of our universe that's a two-dimensional version. We would have to think about a three-dimensional balloon expanding in a four-dimensional space. And for most of us, that's very challenging. And it's really easy to see the 2D one. So think about it as if you're walking on the surface of the Earth, and you're only confined to the surface. You can't move up and down.
Yeah.
And it's a mathematical model that's a simpler version to visualize of what the equations describe, which is a three-dimensional surface expanding and things moving apart.
Right. And so the uniformity that we see both today as well as the cosmic microwave background radiation, we can talk a bit about that. The uniformity, I understand it's something like 1 in 100,000 or something along those lines. So really, really minute variations. lead us to believe that, and because, as you say, the regions didn't have time to communicate with each other, that uniformity is puzzling. So one of the solutions to explain this is that universe went through an inflationary phase very, very early in its progression, right?
That's right. And the inflationary phase makes a couple of interesting predictions. One
Yeah.
prediction is that this enormous expansion and stretching makes things nearly uniform.
Hmm.
The other prediction, which is, I think, to me, the most interesting one, is that rate of expansion, because of quantum mechanical fluctuations, will vary slightly from place to place. Those
Yeah.
slight variations in expansion rate will eventually lead to slight variations in density. So, as you
Hmm.
said, the universe is close to uniform, but we do see variations in the microwave background at 1 part in 100,000.
Yeah.
And we've measured them, and this is what we did with the WMAP experiment. This is what our colleagues have done, our European colleagues, with the follow-up Planck experiment,
Hmm.
and what we're doing right now in Chile with the Atacama Cosmology Telescope is we're mapping these fluctuations in tremendous detail. And while the
Yeah.
variations in temperature are a few millionths of a degree, we've measured them with great accuracy. And to my great surprise, and I was one of the people who had the pleasure, the honor of being some of the first people to analyze this data, um,
Hmm.
the fluctuation statistical properties are as simple as you can imagine. The
Hmm.
basic properties are described just by an amplitude. The
Hmm.
distribution's what we call, a Gaussian. It's a very smooth distribution characterized by just uh, the amplitude of how big the fluctuations are. The
Yeah.
amplitude varies with scale in a very uniform way. And
Hmm.
remarkably, if you look at the implications of the inflationary model, which was kind of introduced in the 1980s by Alan Guth and Andre Linde and others, the predictions of that model on the fluctuation properties are beautifully matched by the data that we observed
Hmm.
in the past 20 years. So this is one of the reasons that a lot of people take the inflationary model quite seriously, because it not only answers these questions that we had before we had the data in the microwave background about
Yeah.
why the universe is so uniform, but correctly predicted the statistical properties of the fluctuations that we see on measured at tens of millions of independent points on the sky.
Yeah. So, so one issue perhaps is that certain parameters of the universe at least appear to be very finely tuned. And I guess the inflation does it make? Let me ask you in a question, David. Let it because of inflation, the initial conditions, whatever existed at time equal to zero, did not matter. At the end of that inflationary epoch, you would get what we observe today. So the initial conditions are not really fine tuned. It's just sort of an after effect of inflation.
That's right. And if you start with a universe that is close to uniform, that has
Yeah.
in order for inflation to happen, it can't be highly fluctuating. It has to be a patch of the universe that's relatively smooth.
Mm.
Inflation stretches things out and erases irregularities. Again, to go to that image of an inflating balloon, you can
Yeah.
start with a balloon that has some ripples on it, right? And
Right.
I pick up my balloon, uninflated balloon, it's not that smooth. But as I inflate and stretch the balloon, as I
Mm.
stretch it, it becomes more and more uniform. And that's what inflation does. It makes the universe more uniform as it expands.
Right, right. And so we don't have a competing theory that gets anywhere close to inflation that sort of agrees with observational data. And if you accept that as as the theory, then what sort of expectations of we are 13.8 billion years in time? How do you think this is, the universe is going to expand further and ultimately end?
Well, this is a question we don't know the answer to, but we're trying to understand as best we can by measuring the expansion rate of the universe to high precision.
Yeah.
At some level, in the context of the general relativity, there's two possible endings. And there's this famous Robert Frost poem, and about some say the world may end in fire, others say in ice, which was based on, I believe, discussions he had at the Harvard Faculty Club with Harlow Shapley, who explained to him the current ideas, I think back then in the 40s, about general relativity. Maybe been earlier. So the one possibility is that the universe expands faster and faster, gets emptier and emptier, colder and colder. So the universe in that case expands forever, but ends up eventually nearly empty, very cold. And that's sort of the cold death of the universe. The second possibility is that expansion stops, turns around and starts to contract. And just like the universe began with that at one point at the Big Bang, we can now think of basically deflating that balloon, and that balloon deflating and shrinking back to zero again.
And that's what's called the Big Crunch.
That's the Big Crunch. And that's as the universe contracts, it gets hotter and hotter. So that's the heat death of the universe.
I was thinking, David, that in a lot of the ancient cultures, this was the notion that you have some kind of a periodic universe, that expands and then comes back to a big crunch and starts all over again. And we don't really have any data that tells us that is the case, right? That could be the case.
We don't have data showing that the universe will turn around and end in a big crunch. There are, as I sort of mentioned earlier, alternative models. And in the case of sort of a cyclic one of expansion followed by contraction, followed by expansion, and then contraction again, the most detailed ones have been developed by Paul Steinhardt and Anna Ias. And they would claim that their model can also explain what's seen in the microwave background, but does require these modifications to general relativity. So that they are people working on alternatives that go along that path. One of the interesting distinctions is the inflationary model predicts during this period of expansion. And remember that different regions expand at slightly different rates because of quantum mechanical fluctuations. That process generates gravitational waves. And those gravitational waves have wavelengths that are the size of the visible universe. Now, one of the great areas of excitement in astrophysics has been the detection of gravitational waves by LIGO. So we've seen them on the scales of a black hole or scales of neutron stars. That's exciting and that's important.
That's a few kilometers.
But that's different from the size of the visible universe. So we've seen the few kilometer scale waves. We've not seen them on the scale of the visible universe. If the inflationary theory is correct, we should be able to see them. One of the most exciting areas of experimental cosmology right now is the search for gravitational waves in the microwave background. That's sort of the next big step in microwave background studies. If we were to see the gravitational waves, that would rule out this bouncing cosmology model and would be strong evidence for the inflationary model.
And one way to do that is through polarization.
That's correct. By looking at the distinctive pattern that gravitational waves produce in polarization. So when you think of polarization patterns, the picture to have is throwing down a bunch of lines at each different point in the sky. There's a direction in which polarization points. That pattern, we can look for its symmetries. We can reflect it in the mirror, and if it looks the same reflected in the mirror as it does unreflected originally, that has what we call E-mode symmetry. It has this reflection symmetry.
And I know that there was
density produce reflection symmetry. Gravitational
Yeah.
waves do not. They produce what we like to call B-mode polarization patterns. And we're looking for these B-mode patterns and have not yet seen them. But one of the big pushes that we're working on is improving our sensitivities by more than factor 10, close to a factor 100 over what we've achieved to date. And with that, the hope is we will see this signature from the very early universe of inflation.
There was a bit of a false alarm, right? Was that BICEP in the South
That's
Pole?
right. The BICEP experiment was looking for this. They saw something with the right pattern, but what they did not show was that the signal was there at many different wavelengths, and they were confused by dust. It's in a way, it's like looking out the window and thinking you see something exciting in the distance, but really it's just a dust smudge on the window. And their signal turned out to all be due to dust in the galaxy.
Dust in our own galaxy.
So it was stuff nearby. It was dust in our galaxy. I was one of the people who, as soon as the results came out, was very concerned that it might be dust in our galaxy based on the data they presented. They had a big press release, but weren't so careful about doing their analysis. And as more data came in from the Planck satellite, even with the existing data that was available before that, it was pretty clear that it was galactic dust.
So this is something, so the Atacama Cosmology Telescope, that is still targeting to solve this problem?
So the Atacama Cosmology Telescope is actually focused right now more on studying fluctuations on smaller scales in temperature and polarization, using that to measure the basic properties of the universe, its density, temperature, its composition, and so on. What we're planning to do is build a follow-on to the Atacama Cosmology Telescope called the Simons Observatory. It's funded by the Simons Foundation, and its goal will be to go after gravitational waves from Chile. And at the same time, the BICEP group is continuing its work, having learned to do this at multiple frequencies to detect dust, and they're also achieving increasing sensitivities. And there are several groups in the world also pursuing this. There's a group in China working in Tibet. There are plans to build next generation satellites. There's a Japanese group building a satellite called Lightbird that will likely have European and US contributions that will go after this by space.
So an observation of gravitational waves at that scale, either through polarization or some other method, will pretty much prove inflation, right? Because you can't have that in other suggested theories.
That's our current understanding, that this would really be the final piece of evidence for inflation having occurred. I think if we were to, right now, the data is very much consistent with the inflationary theory. It made a number of predictions, and what we saw in the temperature measurements are quite consistent with it. And with that, we've eliminated many other possibilities. One of the things that I worked on early in my career was the idea that cosmic strings, phase transitions in the early universe, could produce the galaxy structure we see today, the large-scale structure, and explain what's seen in the microwave background. And I looked at another set of ideas involving other phase transitions producing textures. And those were models that were worth considering. One of our jobs as scientists is to consider models, work out their implications, and see what they are. And sometimes the universe fits our models, and sometimes it doesn't. And I think it's equally as important to find the times when it doesn't as when it does. When it doesn't, you learn what models to discard and then move on.
Yeah, yeah. There is also a third alternative for the end of the universe, right? It's sort of the universe expands even faster and ultimately results in what's called the Big Rip. And so this is a situation where everything flies off and it gets ripped off. Space-time itself is getting ripped off, right? I mean, it seems very elegant to me, David.
I don't know. I'm hoping that we don't end in the big. All of these things happen billions of years in the future. So right. So no one listening should worry that they will experience the universe being torn apart in the Big Rip. If you have, you've lived at least 5 billion years. So
right.
That's not, and it's not an immediate threat.
5 billion, that's all. So that is, in that scale, that's actually pretty short time. So this will be sort of a runaway.
It's a runaway expansion. Once it starts,
yeah.
It really takes off. But all right, so what happens, and this sort of brings us now to some of the things I'm working on now, is we want to know what are the properties of the dark energy. So one of the remarkable things about our current cosmological model is that it's both very simple and very strange. It's simple in that a model with 5 basic numbers: the density of atoms, the density of matter, how lumpy that early universe is, and how it varies with scales, those 2 numbers that come out of inflation, and the universe's current age. With those 5 numbers, I can fit all of the observations in cosmology, basically. That's all I need, and that's, lots of observations. That's a remarkably simple model. On the other hand, it's a strange model, in that it implies that the universe is mostly made up of dark matter and dark energy. Atoms make up only about 5% of the universe. The next 25% is in dark matter. That's some new particle we haven't seen yet. And the remaining 70% is in energy associated with empty space, what we call dark energy. And the universe's fate depends on the properties of dark energy. If the dark energy density stays the same with time, so as the universe expands, the energy in empty space stays the same per unit volume, that's a vacuum energy or a cosmological constant, then the universe will have the cold death we talked about. It will expand forever. If the universe, as it expands, the energy in space grows, so that the amount of dark energy per unit volume gets larger and larger as space expands. Well, that makes space expand even faster. And that creates more space with more dark energy that drives even faster expansion. And it's that runaway process that eventually tears the universe apart in the Big Rip.
So this is the same cosmological constant that Einstein had, and then he set that to 0, and then we had to bring it back because observations showed things are expanding faster.
That's right. So Einstein, when he wrote down his theory of general relativity, realized it predicted an expanding universe. He wanted to stop the expansion because he thought that the data didn't describe expansion. He didn't know that at the same time he was working on this, that Hubble was developing his data showing the universe was expanding. So this was what he called his greatest mistake, that not predicting this. When we could then go back and look at that, and look at that term, and now not evoke it at the level that Einstein wanted, but still put it into the equations, and we can see that it could behave like this dark energy, like this vacuum energy. And our current data is the simplest model that fits all the data is to say that the universe is filled with this vacuum energy. Now, we don't know why that vacuum energy is there. It's a very tiny energy per unit space. It's something that if we had a complete theory of quantum gravity, one of the things it should predict is that energy. In many ways, I feel what we've done is we've made a measurement that particle physicists in the future will need to fit. They will need to explain why it has that value. And we as cosmologists have laid down a challenge to our particle physics colleagues to explain why the universe has those properties.
Yeah, and it's a big, like you say, big chunk of it, 70% of it. So it is, it's very unsatisfying from an understanding perspective, and so that makes it interesting.
It's a big hole in our understanding that we don't know what that is. So, but one of to go back to this fate of the universe, we'd like to know how does the energy change as the universe expands, and what that requires we do is we measure the expansion rate of the universe quite accurately. And one of the things I've been working on is helping NASA to develop and build a new telescope. A telescope we used to call WFIRST, but we recently named the Roman telescope after Nancy Grace Roman, who was the first director of astrophysics at NASA, one of the real founding figures in the history of NASA, a real pioneer. And we were all very happy when we were able to name it after her. This is a pioneering experiment, we hope. So this is a mission that we're planning to launch in 2025. It's using a telescope that was originally developed for the U.S. military as a spy satellite, National Reconnaissance Organization. It's a Hubble-sized telescope, so in terms of image quality, except for the field of view is more than 100 times bigger, and for carrying out surveys, it can cover the sky between 100 and 1,000 times faster than the Hubble telescope. With the same quality image. So when I hope after we launch it, we will be able to survey the entire sky. So we will actually have an image of the entire sky with Hubble quality imaging when we're done.
And you ran into a little bit of a funding issue, I gather.
We have had, the James Webb Space Telescope, very challenging, very important project, has experienced a number of delays. As it experiences delays, it has cost overruns. The president has proposed several times to solve for those cost overruns by canceling the WFIRST mission. Fortunately, we've had very good bipartisan support. Both the Democrats and Republicans in the House and the Senate have supported the project. And with their support, it's been restored to the budget for the past 3 budget cycles. So we have been, with congressional support, fully funded and have managed to stay on schedule.
This is an important thing because one of our primary objective here is really understanding dark energy, right? In Roman telescope.
So the Roman telescope, I think of as having 4 main science programs. One is understanding dark energy. The other is it has a coronagraph that lets it image planets around stars and we will be a major advance in chronographic technology. So this will lay the groundwork for the ability for the follow-on telescope to Roman to be able to image Earth-like planets around other stars. We will not get to those sensitivities, but we might be looking at imaging Jupiter-like planets.
And we have seen through other techniques thousands of these exoplanets, right? So will you be able to actually characterize them?
So that's the third leg. So right now we've been detecting planets with missions like Kepler and TESS that are very good at detecting planets inside the orbit of Earth around other stars. So it's good at detecting other Venuses. We will be using what's called gravitational microlensing to detect planets. And this is a very powerful technique for detecting planets out like Mars or Jupiter or Saturn or Uranus, planets further out. So far we've been studying inner solar systems. WFIRST will study outer solar systems. And by combining that, we will have a much better picture of the demographics of extrasolar planetary systems and have, be able to detect orphan planets. That's an exciting area where we have planets that were kicked out of their own solar system that we should be able to detect in large numbers. So that characterization of properties of planetary systems is our third leg. And the fourth leg is, you might imagine, if you can image the whole sky at Hubble resolution, there's a tremendous wealth of astrophysics, from studying nearby galaxies to planetary nebula to distant systems that we will learn about with the WFIRST telescope. I think it will be a very worthy successor to the very powerful Hubble telescope.
Yeah, a lot of very important objectives. So if you have a brighter star, David, so the habitable zone, as we call it, for life, it could extend further out, right? So we haven't been able to look there, but Roman would be able to do that.
That's right, because we'll be able to do direct imaging of stars regardless of their brightness. Much of the way we've detected planets is through either radial velocities, which you can't do around some of the more massive stars because of the properties of their atmosphere, to looking at occulting planets, and those are always quite close to the star. The habitable zone
can we detect
is the zone of distance from the star in which water could be liquid. We believe that water is essential to life, and the brighter the star is, the more massive the star is, the hotter it is, the further away you want to be at the right temperature for life.
Right. Can it detect atmospheres too? Can we actually see what might be in there?
If we're very lucky, we might be able to do some atmospheric characterization if there are planets around the closest stars and the things are right. It's that right now is sort of just at the limit of what the technology on Roman will be able to do.
Okay. I want to touch on a few of your recent papers, David. One of them is entitled, "What's the Price of Abandoning Dark Matter? Cosmological Constraints and Alternative Gravity Theories." And so you say any successful alternative gravity theory that obviates the need for dark matter must fit our cosmological observations. Coming as an engineer who have moved away from engineering a long time ago, whenever I hear something like dark matter, my intuition is to say the theory has to be wrong. Right?
Yeah, no, I think a lot of us look at that and say, you tell me atoms make up 5% of the universe, and you've got to evoke dark matter and dark energy, there's got to be something wrong with your theory. And to go on a historical detour quickly, if we look at the history of Newtonian mechanics, we looked at the orbit of Uranus and noticed Uranus's orbit wasn't right. So we posited some new piece of matter out there we haven't seen yet, a new planet. And we went out and looked, and it was Neptune, and we found it. So that was a great
Right.
success of positing dark matter and seeing it. But then on the other hand, we saw anomalies in the late 19th century in the orbit of Mercury that we could not explain. And some astronomers invented a new planet, which they named Vulcan, which was supposed to be inside of Mercury. But that new planet didn't exist. Instead, what we needed was a new theory. And that new theory was general relativity. So when general relativity now predicts the existence of dark matter, a lot of people ask, could that be telling us now that general relativity is failing? And the point of our paper is, well, if you want to replace general relativity with a new theory, that new theory has to get lots of things right. It has to get right the expansion of the universe. It has to be able to explain the gravitational waves that we saw from LIGO, and the fact that the gravitational waves that LIGO detected from a neutron star merger arrive the same time as the light that we store from the star. So with the speed of gravitational waves and the speed of light have to be very close. That's a very restrictive, that's predicted in general relativity, but most alternatives to general relativity do not predict gravitational waves. And if they do not predict that they move at the right speed. So you have to go through that hoop. The hoop that we wanted to emphasize in our paper was that when we look at the microwave background, we're seeing the universe 380,000 years after the Big Bang. That's showing us the large-scale distribution of atoms. Shows what they look like early in the universe's history. When we look at galaxies today, we see how atoms are distributed on large scales. If I have an alternative theory, it's going to have to explain how to get from what we see in the microwave background, the universe's baby picture 308,000 years after the Big Bang, to what we see today. And any theory that does that, what we tried to do in the paper was develop the mathematical properties of the theory. Any theory that does that would have to have certain properties. And one of the properties that we show is that the strength of gravity would have to vary with scale, so that it was sometimes gravity was attractive at one scale, it was repulsive at another, then attractive at another, and it would have to keep changing signs. The behavior of gravity in any alternative theory would have to be very strange. So any replacement for general relativity would seemingly have to be very contrived. And we wanted to sort of clarify how difficult this hoop was to go through.
Right. Yeah. And very complex. And so you have another paper here, David, identifying the degeneracy of dark matter, dark energy interaction theory space. And here you're talking about the cosmological constant. There was some suggestion that to replace that with a scalar field motivated by the newest ideas in string theory. And again, you're looking at it as, is this a feasible thing, right?
Yes,
I mean,
when we have these ideas like dark matter and dark energy, it's almost our obligation as a theorist to start to explore the possible things that might be there. So we have looked at things ranging from, could the dark energy evolve with time? Could the dark energy interact with dark matter? Could the dark energy interact with neutrinos? Could the dark matter have significant self-interactions? That's something that we posed almost 20 years ago that's generated a lot of work. And one of the things I'm working on right now is, could the dark matter in its own way behave a lot like nuclear matter, in that there's you have things like neutron stars form out of dark matter that are much larger. So we've been, in a series of papers, I and other people, and many other people are working in this area, explore ideas on what the dark matter and the dark energy properties might be, primarily with the goal of, understanding the possibilities of the theory, but really ultimately thinking about what are the smoking gun observations that will convincingly show what's going on, right? To go back to the history of astronomy in the late 19th, early 20th century, we either would like to predict where Neptune is, where the dark matter is, and have an observer go and detect Neptune, or if we have a theory like general relativity where we have an alternative, we'd like to predict a decisive observation. In the case of general relativity, that was the eclipse expeditions of 1919 that showed the bending of light by the sun, one of general relativity's novel predictions, whose confirmation really meant that in 1919, physicists started to take this remarkable idea of Einstein's very seriously.
There was something in the news, I believe, David. I think this has been kicked around for a while. The idea that there were a lot of primordial black holes, small ones perhaps, that is really the substrate for dark matter. Is that something that is possible?
One of the plausible candidates for dark matter is lots and lots of primordial black holes produced in the very early universe. There has been an very active program over the past almost 30 years of exploring this idea. We've ruled out large ranges of masses. So if the mass was of order the mass of the sun, we would see it through gravitational microlensing. If its mass was 1,000,000 times that of the sun or bigger, it would have effects in our galaxy and in dwarf galaxies and in the Lyman alpha forest that we would have detected. So I think we can rule out very massive black holes. If the mass was extremely light, less than 10 to the 14 grams or so, I think is the cutoff, a light black hole would have actually evaporated by Hawking radiation, so it would not be around anymore.
So it has to be in between those two numbers.
There's debate about whether there are black holes between that minimum mass and, say, the mass of the Earth would be allowed. People discuss detecting them through X-rays, detecting them in other ways. So there's an active debate whether it's a viable black hole, a viable dark matter candidate.
This is somewhat unrelated, but there was some excitement about the Planet 9 is actually a black hole. What is your feeling about that?
I'm not yet convinced that Planet 9 must be there. There is some intriguing evidence based on the orbits of some of the what's called Kuiper belt objects. Those are objects, small planetesimals like Pluto, out in the edge of the solar system, small kind of leftover rocks from the formation of our solar system, that there could be a Planet 9, a massive planet, perhaps the mass, 5 times the mass of Earth, which is much bigger than Pluto, wandering around out at 200 to 400 times the distance of the Earth from the sun, and that would explain things, and that's this Planet 9. All we can do is see that it's there through its gravitational effects. So that could be a black hole. I think it's far more plausible because we've never seen black holes of that mass. We do see around other systems lots of planets of order 5 Earth masses. We know that our solar system is nearly full gravitationally. If I put in a 5 Earth mass planet to say between the orbit of Uranus and Neptune, it will get ejected from the solar system and might end up far out like that. So it's a plausible idea. We're actually actively looking for Planet 9 right now with our microwave background satellite and telescope in Chile. So the Atacama Cosmology Telescope, which is primarily studying the microwave background, is scanning the sky at microwave wavelengths. If there was a Planet 9, it would be emitting in the microwave. So one of my colleagues, Sigurd Ness, has been combing through our data, looking for Planet 9 in the microwave. Once the Rubin telescope, a large optical ground-based telescope that's surveying the sky, goes online, it will be surveying much of the sky from Chile and starting in just a couple of years, and it will be able to detect Planet 9 in the optical. So I think if it is out there, and if it is a planet as opposed to a black hole, we will be able to see it directly within the next few years. So I think, I would say it's plausible. I mean, I would give basically even odds that in the next decade, we will see a newspaper headline, Planet 9 detected.
Yeah, you're also doing a lot of work actually applying machine learning techniques. So all of these experimental things are going to generate tons and tons of data. And unlike maybe 10, 15, 20 years ago, we can now deploy machines to maybe comb through that and look for patterns and even create hypotheses and learn from it, right? So I was looking at one of those papers, David, predicting the long-term stability of compact multi-planet systems, where you say you combine analytic understanding of the dynamics in a two-planet system with machine learning techniques to train a model capable of robustly classifying stability in compact multi-planet systems over long timescales of orbits. You want to talk a bit about that paper?
I think of this to put into context. There's been a real revolution in the past decade or so, driven by the development first of faster computers, the availability of large data sets, but most importantly, advances in new algorithms in machine learning that have enabled us to sort of use it to learn novel things about new data sets. And the classic example I think about machine learning is you hand the neural net hundreds of thousands of pictures of cats and dogs, and each picture is you can think of as it's an image with 1 million pixels. So it represents one data point in a 1 million dimensional space. And with only a few thousand, maybe tens of thousands of data points in a 1 million dimensional space, which is a huge volume, the neural net is able to learn the difference between cats and dogs. And you give it a new picture and it classifies it. We're basically doing a very similar project. We're looking at multi-planet systems. There are many different ways of combining multi-planet systems. We run complete computer simulations that tell us whether a particular multi-planet system is stable or unstable. And we use that to train the neural net. And just like the neural net can distinguish between cats and dogs, it can now distinguish between stable and unstable planetary systems.
So just like anything else, just like you said, a supervisory machine learning technique, you say these are stable, these are not stable, learn from it, and then go look for a new one and assign a probability.
That's right. Now, the advantage we have in physical systems like this is we sort of have 500 years of physical or 400 years of physical understanding since Newton. And so we've been thinking about the planetary stability problem for a long time. So we know that there are useful ways of thinking about it, things like resonances and things like that. So when we train the neural net, we train it on information that we already know is valuable. So that and this is one of the, for people thinking about machine learning, one of the interesting things about physics problems is we have a lot of intuition and understanding about what matters in a problem. Often it's the symmetries of the problem. And then you want to structure your neural net so it takes advantages of some of this information.
So you could actually sort of envelop the raw data with some human annotated features. And then make it learn. So that could be the downside. Obviously, sometimes is we bring some biases.
So this is the discussion I've had many times with people who work on machine learning. Is the lesson they've learned from areas that are more uncertain. If we're looking at applying machine learning to something like our understanding of COVID, which has been evolving and growing with time, you don't want to be driven by your biases. But as a physicist, we know that mass is conserved, angular momentum is conserved, the universe is symmetric under rotation, and those things we've tested, depends how you quantify it, but at parts in the billion or trillion level. We have kind of a precision understanding of the symmetries of nature that we know our data is not going to violate. And so we feel pretty comfortable taking advantage of those symmetries and using summary statistics based on those symmetries to describe what's going on.
Yeah. It's an exciting area. So in conclusion, David, I know that you're intimately involved with the Roman telescope project. If you look forward 5 years, 10 years, what would be sort of the discovery that you would be most excited about?
Well, from the Roman telescope, what to me would be the most exciting result is to see that dark energy is evolving with time, that it's not a constant, and that we're seeing it either grow with time, suggesting we need to worry about a big rip eventually, or shrinking with time, suggesting that this period of dark energy dominance is but a stage in the universe's evolution, and different things will happen in its future. Either one of which would be incredibly exciting, would give us new insight into the nature of space-time. So to me, it's certainly not a guaranteed result, but to me, would be the most exciting result I think we could hope for.
And the horizon is like 5 years. Is that you would start getting data in that time frame?
It'll take longer, of course, to get the data, to analyze it. If we see something that dramatic, it will take several years of data to be really convinced that's what's going on. But we're moving towards it.
Excellent. Yeah, this has been great, David. Thanks so much
pleasure.
for spending time with me, and good luck with all this research.